Okay, so now that we realize that we are going to have to shift our thinking about how we find out information about the electron due to quantum mechanics, it turns out a lot of the information we are actually going to get from a very complex equation known as the Schrodinger equation, depicted here. Now, what we're going to really focus on most of the time are the quantum numbers that we get from these equations, and also this fact that we can plot the distance from the nucleus as a function of versus the wave function symbolized by the Greek letter psi. So a plot of distance from the nuclei versus psi squared represents an orbital, sort of the terminology used from Niels Bohr first, atomic theory. And this represents the probability distribution of where we can find the electron to be most likely found. Okay, so this is going to give us the best idea of where the electron is within an atom. Okay, and the first quantum number that we get from Schrodinger equation is the principal quantum number, which we will refer to as n. Now it turns out that n can be any integer greater than equal to 1. So n for a given atom can be 1, 2, 3, 4, so on and so forth. Okay, it corresponds to the energy level as we saw in Bohr's model, and so that the higher the n value, the higher the energy of the electron. Okay. In addition to that, as we'll see, the n value can also give us information about the size. Because if we know that the higher the energy value, n, the more energy that electron has, we know, or we'll see, that the closer the electron is to the nucleus, the more stable it is, therefore lower energy. So the higher the n value, also we can assume that the size of this orbital, as we'll see, is also increased. It's further away from the nucleus. Okay. So here's a new, better, in my mind, depiction of what occurs when that electromagnetic radiation was emitted from, say, the hydrogen lamp, or helium, or barium, or any other material, atom or molecule that emits energy. So if you have an electron at n equals 1, and you excite that electron, it goes up to n equals 3. It's a higher energy, further away from the nucleus. Eventually, that electron will want to become more stable and fall back down to a lower energy level. When it does that, it emits a photon, which we depict as h nu. Okay? And again, that wavelength of that photon corresponds directly to the difference in energy of those energy levels. Okay, so let's look at an actual example. Here's the energy level for the hydrogen atom, and it gives specific energy values associated with the electron. Okay, n equals 1, n equals 2, n equals 3, and n equals 4. Notice that as the n principal quantum number increases, the distance between those energy values, or the difference between those energy values, gets smaller. The biggest jump is from 1 to 2 energy levels. Okay, so let's do a calculation for figuring out the wavelength associated with an electron. Okay, let's say there's an electron down in n equals 1. And just as we saw here, let's say we excite that electron to the third energy level. When it falls down to, say, the second energy level, it's going to emit a photon. Now, the energy of that photon will equal the energy difference between those values. So n equals 3 energy values minus the energy associated with the second energy level. Okay? And we can calculate that the energy just by using those values depicted here. So a negative 2.42 times 10 to the negative 19th joules minus a negative 5.45 times 10 to the negative 19th joules. Okay, that will give us an energy of 3.03 times 10 to the negative 19th joules. Okay, so that's the energy difference between these two energy levels. And again, the energy is going to match the wavelength of that photon. So now we can do that. We can calculate the energy, or excuse me, the wavelength of the photon. So what is the wavelength of that photon? Okay, so we know we have this equation, E equals h nu. We know the energy of that photon, so we can calculate the frequency of that photon by dividing the energy by Planck's constant. And so the energy we just calculated was 3.03 times 10 to the negative 19th joules. Planck's constant is 6.626 times 10 to the negative 34th joules times seconds. Joules is going to cancel out, so that's going to give us a frequency in reciprocal seconds of 4.57 times 10 to the 14th hertz, or reciprocal seconds. Now that we know the frequency, we can of course calculate the wavelength by dividing the frequency by, or the speed of light by the frequency. Okay, so the speed of light again is 3.0 times 10 to the 8th meters per second divided by the frequency, which we just calculated, 4.57 times 10 to the 14th reciprocal seconds. Seconds is going to cancel out, and our final answer, our answer for this calculation will be in meters, and that will give us 6.56 times 10 to the negative 7th meters, which, if we convert to nanometers, because this happens to be in the visible wavelength of spectrum, a wavelength of 656 nanometers. And since we discussed this, that was one of the wavelengths of hydrogen. We can see that what we did was calculate the wavelength of that red light that we saw from the hydrogen lamp. You can see that there's other wavelengths associated with those that we could have calculated, the N4 to 2 transition, 5 to 2 transition. Of course, the electron can fall, say, from 3 all the way down to the ground state, as we call it, n equals 1. It just so happens that, of course, these energy transitions are much larger than these. And so these are in the UV vis, or the UV region of the spectrum. So these are UV photons. Okay, smaller electron transitions, say 5 to 4, or 5 to 3, 4 to 3, are IR photons. Okay, and of course, the calculations for those wavelengths would be the exact same as the one we did for n equals 3 to n equals 2. Again, the wavelength of those photons matches exactly with the difference in energy of those transitions from one energy level to another.